let us continue. So we covered only position control. But if you want to create a robot, not just to follow a predetermined trajectory, but to do something useful, we also need to consider force and hybrid motion force control. What is the idea? The idea is the following. Can you apply force to, I don't know, this point? Let's assume that this is a point. I cannot just apply force to just nothing. I can apply force only to another body, right? So force control can be used only if our robot is stuck and do not move. Only, for example, my arm. Now I use position control. I touched the board, and right now I can switch to force control, and I can apply force. So force control can be used only there. And this is why force control actually is something ideal, and pure force control, we do not use pure force control, only in combination with the position control, or which is something called hybrid position force control. So let's assume that the only thing that we want is just to apply force to this board. We have a robot, and where our robot is. Let's assume the same picture. Let's assume that we have a force here, reaction force. If we multiply force with velocity, what will we get? Power. In order to tackle this force, we need to produce the same power, but means of our motors. So here we can apply torque, tau 1, tau 2, and those components are supposed to be equal. Now we know that velocity actually equals to Jacobian times angular velocity. Do you agree? Force, maybe better, times velocity equal to tau times angular velocity. Okay? We know that velocity equal to Jacobian times angular velocity. We just considered this thing. We can put it inside. So we can say that this thing equal to this thing. So Jacobian tau transpose equal to the force transpose equal to the Jacobian. And out of here we can say that torque equal to the Jacobian transpose times force. Like this. Okay? So Jacobian describes the Jacobian describes geometry of our system. Force is any function that we want to any force that we want to apply to an object. So we can put here anything. So this is the idea. And if we put here something specific, we can call it an impedance control or hybrid motion control. So the idea of impedance control or hybrid motion control is just like we attach a virtual spring, another case with this equation. So it's like I will create a new drawing. So we have a robot, and assume that we want to go right here. It is the desired position. This is the actual position of end effector. And we can think like we have a virtual spring and virtual damper that attached our end effector right here. And this spring pulls end effector right here. So if there is a difference between an actual position and desired one, it's generate force which is applied to the end effector. And we can say that this force for the impedance can be calculated as the coefficient of stiffness times the error in position plus damping times delta p, pretty much the same equation. But here it will be a vector, and k and d will be matrices. It's not a scalar anymore. Here delta p is a vector of 2, px and py. So k will be, you can have a scalar here, but it will be just the same coefficient for the x and y, or you can use different numbers for different axes. So just like this. Okay, let us have a small demo. By the way, you also will have time to take a look at it at home. I will send you these models. So here you also can see pretty much the same motion. It's not such not very fun, but if you take a look at model right here, you will see that now it computed differently because we have this impedance block, and this impedance block I just computed this component. Okay, so tau equal to J transpose, so this prime dot prime, it is transpose, times force. Force is computed here, velocity, it is Jacobian times angular velocity. Here you can see the Jacobian. Okay, coefficients of control k and d. If you do only this component, it will be not such a good idea because we also have gravity, and this is why we use also gravity compensation. So I also have an additional block here which is called dynamics, but I left here only T component, or N component, the gravity. I have to say that it's a very simple implementation of the hybrid control, and I encourage you to consider reading this chapter, robot control and hybrid motion control, in the book of Kevin Lynch. And here you also will find out a lot about it. And here you can see the Jacobian transpose and huge equation for the force. And it's like a proper way how can you do hybrid motion control for any kind of robot with this, even with the spatial mechanics. And here you can see the gravity component. So there's a lot of words is written here. So I encourage you to read because it's just amazing how great the chapter is written. Okay. So we now consider what will be the second practice task. So actually you need to do the same as I already showed you, but all examples that I give you, and I will send you all the models that I showed you, those were for a robot with the 2 revolute joints. You will have the following. So it's like first problem, revolute joint, and the one prismatic joint, then prismatic joint, revolute joint, and with 2 prismatic joint. So you will be given with one of these. And your task is to do position control using PID, position control using model-based control, and also implement this impedance control. Okay?
And you can choose whatever you want?
No, you will be provided with examples, with the tasks. Those are randomly generated, so it's not ready yet, but let me show you.
It's like the video in YouTube? It's like the lecture on YouTube?
Yes, it will be according to the lecture, but I will provide you the guideline. It's not finished yet, but let me show you. So you need to defend your tasks until we have practice lessons, because we don't have them a lot. It's like 4 practice lessons we have. If we'll need, we will arrange additional lessons, but I want to do I do not want to create a lot of consolidations, but whole practice we use them for the defending. All right, so for example, here you can see your ISO number, your names, the type of the schematic representation. It is for the first practice task, but for the second practice task it will be the same. So you will be given with the type of the variant. So I have it right here. Type of the, it's not the one, that one. ISO number, type of the mechanism, and type of trajectory. Like you can use, for example, these trajectories or any other kind of trajectory that is different from a circle. It's like a circle is just boring. I encourage you to use any kind of fancy planar trajectories. All right. Is it clear? Okay. So now, finally, we have quiz.